Okay. My dear students, I'm going to give a complex variable and a numerical analysis. So we are in the first sessions. I giving some basic definitions regarding a complex number. You are familiar the number, real number conditions. What's a real number? We know that. Real number, sum of a two real number is a real number. Difference of a two real number is real number. Product of a two real number is real number. Division of a two real number is division. Whatever may be or conditions may be that. The complex is the extension field of a real number. What's a complex number? Yeah. So in the order pair of a real number can also express in terms of a complex number. For example, p equal to x comma y. We can write in express in terms of complex number, we can write x plus iy, where x is a real term, y is imaginary term. We x represent on the x number, we represent on the x axis. Y represent on the y means this is a x is the real part and y is the imaginary part, where I represent in the imaginary axis. That is the term. The sum of a real and imaginary. We are expressed in complex number. We are now in the basic and pure field. See, the basic in a complex view, you take a unit disk. Unit disk means you are express IVA in within that unit circle or unit disk in that. The same way here complex suppose where is that 2 comma 3 I express in terms of complexness 2 plus 3i where I product means imaginary 3 times we express in the y-axis like that. This is the term we are going to give some details in the complex term. So basically we come to the know what the real conditions in the limit functions, etc., word in the realm. The same word in complex term. But before the study of a complex variable, know the limit, continuity, and differentiability. The reader should know the knowledge of some basic definitions which we come across often in the further study of complex analysis. See, if you take a function, we know in the real number conditions, we function define, the variable, we know the constant, we express in functions. So if you take a limit x tends to a, f of x is equal to f of a, this is f of a tends to some non-real number under some constant. The same word in the complex form. What is first? We go for some definitions, then we come to the examples and some problems regarding the complex equations. See, the first session I already told in the first sessions is only basic conditions. That circular domain. If z0 is a complex number and or a positive number, then the set S of a point z such that mod z minus z0 less than r is called a circular domain. See, so I explained in already. If you take a unit to circle z not be any point, in z. If you take a difference, means absolute values of z minus z naught made very small. That small is difference in the circle where r represent a radius of a circle. That is a circular domain. It means all the point lies within the circle. That is called. So if we come to the second definitions, rectangular domain. The set of complex numbers z such that a real part lies between a less than a real part of z, real part of complex number less than b, and c less than imaginary part of z less than d, where a, b, c, d a real number such that rectangular domain and would be denoted by a symbol r. A comma b is to c comma d. The number difference b minus a and d minus c will refer to the length of sides of a rectangular domain. So, if we come to that, suppose if you take a point z, if you take a point z and z naught, where neighbors of that. That's the neighbor points. If we define in complex term, we define in the complex number term, the neighborhood of a point z naught in the organda planes or complex plane. What's the organda and complex plane? We already know. In suppose if we take xy plane, P be any point of that x now y, draw PM perpendicular joint OP. If OP is R represent, so x comma y we can write x plus I bar. This is called organda diagram. We represent in terms of that. So that is right. The neighborhood of a point z naught in organda plane or complex plane is the set of all point such that mod z minus z naught made very small, means mod z minus z naught less than epsilon. Epsilon is called a radius of neighborhood. So we made very small. These negligible numbers, that is the epsilon, very small, that is called radius of, that is called a neighborhood of a point. If we come to the closed disk, suppose if we take a circle, unit disk like that, the set of all points z lying within a region bounded by a circle C covered by a region mod z minus z naught less than or equal to R. This region is called closed disk. This is closed, means all point within that circle. All point, if you choose a number of points, the all number point lies within the circle. This is called a closed disk. The region without its boundary is covered by mod z minus z naught less than R. This region is called open disk. So less than or equal to R is called a closed disk. If a strictly less than R is called open disk. Now, if we come to that, if a deleted neighborhood, what means that a deleted neighborhood? Suppose a deleted neighborhood of a point z naught is the set of point given by mod z minus z naught less than epsilon, except the point z naught itself. So that is it's called deleted neighborhood. So except the point z naught, we left in that point should be z naught. That is called deleted neighborhood. Interior. So we come to that. Interior means, suppose if we take a set of all point within the circle, I call that should be S. Set of all point. The all point in a circle, a bit unit circle line. Consider as set S in a complex plane. A point P belongs to set S. A point P belongs to a set S is said to be interior point of S. If there is a C, a neighborhood of a point P, which contain completely in S, where C is a circle with this lies entirely in S. All the point lies within that set, the unit set. Means we call that. This is called interior point. If we come to the exterior point, so if you come to the exterior point, is omitting that. Means that is not included that point. So a point is said to be exterior point of a set S if there is a neighborhood of a point which does not contain any point of S. That is called excluded. That means we are not taking that point. That is called exterior point. A point is said to be an exterior point of a set S. If there is a neighborhood of a point which does not contain any point of S, that is called exterior. We come to the boundary point. A point is called a boundary of a point of a set S if is either interior point nor exterior point of S. So if the boundary, if you take a Euclidean circle, the circle should be point lies on the curve. Curve means boundary of that. So either interior or exterior. The point is called a boundary point of a set S if either a interior or exterior point of S. Here I am saying this. That's it. There are two important either closed, open, or boundary points. So in the open set, a set S is a complex plane C is called an open set if every point of S is an interior point of S. Every point of S is interior point of S. For example, if we take mod Z minus Z naught less than R is an open set. Means strictly means all the point lies within that R. R means strictly less than. Means if you take any point that belongs to less than that, the interior and the open set consisting of all points within the interior of the region bounded by a circle. So within that, if you choose that all point within that, the unit circle. Unit circle means if I'm saying unit circle means if you're taking a radius should be is 1 like that. This whatever may be a radius 1, 2, 3, whatever. But within that circle, that is called open. If with R radius and center Z naught. So we come to that. We define every deleted neighborhood point, open set, closed set, interior point, boundary point, open set, and closed set, everything. We come to that. Within that, we come to the limit point. What's a limit point? Yeah. Suppose a point Z0 is a limit point of a set S in the organda plane. Every neighborhood of a Z0, however a small, contain infinite number of a point S. The following have some meaning: limit point, limiting point, accumulation point, cluster points. Yeah, this is the same meaning of a limit point. Again, I come to the definitions regarding this is a basic. I'm going again. And in the next session, I giving what is a limit, what is a continuity, what is a differentiability. So in the real number conditions also x plus in terms of a complex conditions also. What's the limit in the complex plane? What is the functions in the complex plane? What is the continuity in the complex plane? What is the differentiability in the complex plane? That is the way. So simply I am saying what's the limiting point? A point Z0 is a limit point of a S is an organda plane. If every neighborhood of a Z0 however a small infinite number of a point S, the following has a meaning of limiting point, accumulation point, and cluster point. For example, if we take the point, a limit point of a set 3 plus 2ni divided by 1 plus n for all n equal to 1, 2, 3, etc. is 2i. So we give a number, we give some cancellations law hold like that. Some cancel numerator and denominator, we get a resultant terms should be equal to. This does not belongs to the set. The limit point of a set may not be belong to the set. So another example we give, every point of a set of all points on a circle is a limit point of a set, because if Z0 is a point of the set, every neighborhood of a Z0 will contain infinite number of a point of a set lying on the arc of a circle which lies in the neighborhood. See, this is so I am giving the within the circle. This is the meaning. So if a Z0 is a point in the Z0 is a point in the set, every neighborhood of a Z0 is a point in the set. Every neighborhood of a Z0 will contain infinite number of point of set lying on the arc of a circle which lies in the neighborhoods. That is the limit. We come to the closed set. A set S is said to be a closed set if all its limit point belong to the set S. For example, the point Z such that mod Z less than or equal to 1 is a close. Less than or equal to 1 means if a center is 0 like that, if a type mod Z less than or equal to that is a unit like in a circle center is 0 like that. A bounded set. What's a bounded set? Suppose we take a set in the reality conditions, f of x is bounded. What do you say? You should choose a positive number such that minus k less than or equal to f of x less than k means f of x less mod f of x less than or equal to k in the real number. The same conditions is what in the complex plane. A set S is said to be a bounded if there exists a finite positive number k such that mod z less than or equal to k for every point z belongs to S. If the set is not bounded, then it is called unbounded set. So in the real node, mod f of x less than or equal to k is bounded. Suppose mod f of x greater than or equal to is not bounded. In the same word in the complex set mod z equal to 1, mod z less than 1, mod z less than or equal to 1 is a bounded set. While mod z greater than 1, mod z greater than or equal to 1 is unbounded set. We can't define. That is default means we give any number, that function is more than that. That is called unbounded set. But what is said to be a connected? You come to the connected set. Set S of a point in the organda plane is said to be a connected set if any two of a point can be joined. If any two of a point can be joined, is continuous curve of all those points belongs to this. Means we know this is a meaning set. Suppose if you take Z and Z as Z1, Z2, it should be a connected set. In the organda plane, if you take a complex plane organda planes, is said to be connected. If you take a two-part, join that on the curve. Suppose if you take unit circle, suppose it takes Z1 and Z2, say join and curve form is called connected set. That's called a connected set. So you come to the open domain and the closed domain. What's it? You already know. If you take a two set domain, codomain like that. If you come to the open domain, what's the meaning of domain within that? A open connected set is called an open domain. Open connected set is called an open domain or open region. If the boundary point of S are also added to the open domain, then is called open domain. Means you are considering in the boundary point. That's all. You are considering open domain is the open region and open connected set is called open domain. Open region if the boundary point of a S are also added. So we are considering a boundary point. That's called open domain. Open domain. So it comes to the next section. This is all our basic. Within that we are saying within the circle model that this we are defined in complex. Come to the function complex functions of complex variable. To each value of a complex variable z, if their corresponding one or more than one value of complex variable w, then we say that w is a function of complex variable z. Also we write w is equal to f of z. W is equal to f of z. Since z equal to x plus iy and f of z will be of the form u plus iy. F of z will be of the form u plus iy, where u and v is a function of two real variable x and y. We may then we write w is equal to f of z equal to u of x comma y plus iv of x comma y. This is a complex variable function, complex functions. For example, suppose if we take f of z equal to z square. For z square, we can write x plus I y square, I y whole square. We can write x square minus y square plus 2I x square. Means I square is minus 1, we can write x square. Here, real terms should be equal to x square minus y square. Imaginary terms 2 times of x square. So we can express u of x comma y is x square minus y square. V of x comma y is 2xy. Here, real part is x square minus y square. Imaginary term is 2 times of xy. Suppose we express f of z equal to sin z. Sin z. So z is sin of x plus I bar. So using trigonometrical functions form sin of a plus b formula, sin a cos b plus cos a sin b. So at the same time you are expressing sin x cos iy plus cos x sin iy. So here again we getting that term. So we now know the in the hyperbolic function sin x cos iy should be cos of hy, hyperbolic function, plus cos x sin of iy we can write I sin hy. We can write again we as the real part is sin x cos hy, imaginary part cos x sin hy, like that. So we come to that the same way. So here u of xy is sin x cos hy, v of xy is cos x sin hy. W is said to be a single valued or many valued functions of z according as for given value of z, their corresponding one or more than values of w. So that is the functions of that. So if we give a single value w, we get more than one or many value function of w. For example, we come to the f of z equal to z square is a single valued function defined any set since z square has only one value every value of z. In particularly z equal to 1 plus I. F of z equal to 1 plus I square. So again we are expressing a square plus b square formula. 1 plus I square plus 2i. I square is minus 1, 1 get cancelled, we get 2i. Suppose if we take f of z equal to z to the power of 1 by 2. This is an example for multiple valued functions. The functions have two value for z. So, functions of complex variable in terms of a limit. We already know that the basic in the limit, what's the neighbors are like that. We come to the definitions of a limit in a complex variable. See, I come to cut. Suppose we give it in terms of in a real form. What's a defined a limit? So, f of x be a function is tends to L as x tends to A. As x tends to A. We write in the limit x tends to A, f of x is equal to L. This is the inner form of a real. We extend the same way we are expressing the complex variable form. Let w equal to f of z be a function of z defined in a bounded and closed domain D. We say that f of z tends to limit L as z tends to z naught. As z tends to z naught along any path in D, if each positive arbitrary number epsilon, however small, their corresponding positive number delta, such that mod f of z minus L made very small for all point z of D for which 0 less than mod z minus z naught less than delta. This is the limit of the complex variable. See, once again I write, let w equal to f of z be any function of z defined in bounded and closed domain D. We say that f of z tends to the L, limit L, f of z tends to limit L as z tends to z naught along any path in D. If each positive arbitrary number epsilon, however small, their corresponding positive number delta, such that mod f of z minus L less than epsilon for all point z of D for which 0 less than mod z minus z naught less than delta. Then we write limit z tends to z naught f of z equal to L. This is the limit of the complex variable. Thus, the above definitions means that there exists a deleted neighborhood of a point z equal to z naught in which mod z minus L less than L can be made small as we please. Note, the limit where it exists unique, whatever be mod of approaches to z naught through the point in S. So these are all lies in that S. So approaching that should be limit exist. For example, I will take a limit. For example, we give limit z tends to 1 plus I. Limit z tends to 1 plus I. Z square minus 5z plus 10. So limit that if you apply, replace z by 1 plus I. So that the function is given 1 plus I whole square minus 5 times of 1 plus I plus 10. Open that 1 plus I whole square, what do you get? 1 square plus I square plus 2I. I square is minus 1, 1 get cancelled, we get 2I. Open that minus 5 minus 5I plus 10. We get 5 minus 3I. This is the direct applying the limit. One more example. The limit z tends to I, x z cube minus plus I divided by 5 minus zi. So we replace z by I, so we get 0 divided by 6. So 0 divided by 6 equal to 0. So replace I z by I. Just I cube should be minus 1 minus I plus I get cancelled in the numerator. Denominator should be equal to I minus I replace I square should be minus 1 plus 1 minus 1 of 1 should be plus 5 plus 1 should be 6. So 0 divided by 6 equal to 0. One more given. The limit z tends to minus 2I 2z plus 3 divided 2z plus 3 into z minus 1 divided by z square minus 2z plus 4. So same way we are express. First, we replace z by minus 2I. So 2 times of minus 2I plus 3 minus 2I plus 1 divided by minus 2I whole square minus 2 times of minus 2I plus 4. So simplify, we get 1 minus 1 by 2 plus minus 11 by 4 times of I. This is simple way you are direct applications. We are applying directly, we get that. Now we come to the one more definitions. If you apply the limit, z tends to 2 times of I pi by 6 z square minus 4 divided by z cube plus z plus 5. So if now this limit is exponential functions, limit is exponential functions. If z tends to 2 times of e power I pi by 6. Now the exponential form. First you take a z equal to 2 times of exponential function. Exponential e power I theta e cos theta plus I sin theta. Similarly, same way you are expressing here cos pi by 6 plus I sin pi by 6. Pi by 6. What's the cos pi by 6? Root 3 by 2. So plus I times of cos pi by 6 is off that. So 2 times of root 3 by 2 plus I times of 1 by 2. Here 2 to get cancelled, root 3 plus I we get. Similarly, if you take square that, 4 times of e to the power of I pi by 3. You square that, we get 2 times get I pi by 6 whole square, we get 2 to get cancelled, 2 times of I pi by 3 divided by 6, 2 times get cancelled, means 4 times of e to the power of I pi by 3. This is the same exponential form, 4 times of cos pi by 3 plus I sin pi by 3. 4 times of, what's the cos pi by 3? If cos 60 is off, plus I times of sin 60 is root 3 by 2. Again we get simplify 2 times of I plus I root 3. Similarly, if we express in terms of z cube, so we get 2 e power I pi by 6 whole cube, we will get 8 times of cos pi by 2 plus I sin pi by 2. Simplify, cos 90 is 0, sin 90 is 1, we have 8 times of 0 plus I is 8 times of I. So if you take a function now, limit z tends to 2 times of e to the power of I pi by 6 z square minus 4 divided by z cube plus z plus 5. Substituting the value of z square minus 4 value of z cube, we get 2 times of 1 plus I root 3 minus 4 divided by 8 times of I plus root 3 plus 1 divided by 3, we get that. The value should be equal to 2 times of I, 2 times of 1 plus I root 3 minus 2 divided by 5 plus root 3 plus 2I. Simplify, we get that. The value should be like that. Now we come to that, the functions of complex variable in a limiting form. So we know in the reality condition, limit point exists, does not exist. The same way right hand limit, left hand limit in the form of a reality. The same way where in the complex form, the limit point exists, might not be existing. Prove that the limit z tends to 0, conjugate of z divided by z does not exist. So the solution, if a limit is to exist, it must be independent of manner in which z approaches to a point 0. Let z tends to 0 along the x-axis is 0. Then y should be 0. Because z equal to 0 means x plus iy, where x is 0, y is 0. Like that, x tends to means x is z-axis. So then y is 0, then x plus iy, x and z conjugate of z, x minus iy is x, so that the required limit is x divided by x equal to 1. In that, so you are expressing this complex number first real axis, then we go to the imaginary. If z tends to 0 along the y-axis, then x is 0, then z plus iy. So x is 0, it then should be imaginary iy. Then z bar should be equal to x minus iy should be equal to minus iy. So that the required limit should be equal to minus iy divided by iy. So we get minus 1. Yeah, observe that. So in the x-axis, the value should be 1. The imaginary term means x-axis is a reality. The real term should be 1. In the imaginary term should be minus 1. So here the limit does not exist. 1 minus 1. So it's not equal. So since the two approaching does not give the same answer in the limit, so does not exist. Another way we can express in the same limit in form, let z tends to 0 along the path. If we take z tends to 0 along the path should be, if we express y equal to mx. So at thus z tends to 0 implies x plus iy tends to 0, x tends to 0. Now limit z tends to 0, z conjugate divided by z is limit x tends to 0, x minus iy divided by x plus iy. So limit z tends to 0, so x minus I mx divided by x plus I mx. So y should be expressing, should be replace y equal to mx. So if we take x as a common, so you get 1 minus im divided by 1 plus im. The value of the limit approach depend on the value of m. Yeah, the value of limit depend on the values of m, which is not unique. Thus f of z approaches the different value along the different radial lines. Hence, the limit does not exist. Come to the one more simple example, so that the limit z tends to 0, xy divided by x square plus y square does not exist. So limit z tends to 0 along a path y equal to mx, that is z tends to 0, x plus iy tends to 0, x plus I mx replace y equal to mx, we get x plus I mx tends to 0, x tends to 0, we replace. So limit z tends to xy divided by x square plus y square. So limit z tends to 0, I x mx divided by x square plus m square x square. So again x square, take x square as common, we get m divided by 1 plus m square. Again this value depend on m. The value of limit depend on m, which is not unique, hence the limit does not exist.